Hi, everyone. We're now going to look at the issue of determining a sample size n before you even conduct a study. So before we draw a sample, it would be nice to know how large the sample size should be so that we have a certain confidence level and a certain margin of error E. So let's say that we want to predetermine both a confidence level, which is typically predetermined, but also the margin of error E. So we're going to select the sample size so that we can pre-select the margin of error. We can do that, assuming that we have a good value for sigma, an accurate value for sigma, which we'll talk about later. So determining the sample size little n for estimating a population mean mu. How do we figure out a sample size so that we can get the kind of confidence interval that we want in terms of its overall properties? So for a 1 minus alpha confidence level, so remember, some common confidence levels are 95%, like 0.95, or 99%, like 0.99. For a 1 minus alpha confidence level and the desired margin of error E, the required sample size little n is given by the following formula. Of course, you won't have to memorize it. It'll be provided to you somewhere, like here, if you're doing homework. Now, you might be wondering what this operator is, this pair of symbols over here. That's the ceiling or round up operator. So for example, let's say that this stuff in the middle, let's say that this argument in here, the stuff in the middle, is 899 on the dot. 899 exactly. Well, if that's the case, there's no rounding to do. You just grab the 899 as your sample size. So if this over here, if this piece in here is an integer greater than 30, because remember, we would like the central limit theorem to kick in. We're not sure if we're going to have an initial assumption of normality. So it would help a lot if this were to be greater than 30. So if the integer is 899, we just grab that integer as our sample size. Now, if you get let's say 899.1, something like 899.1. Well, this operator, this pair of symbols here, will tell you to round up. So round this up. That's what the ceiling or round up operator does. Round up to 900, the next integer. Again, that's a way of being conservative, playing it safe. When in doubt, to play it safe, make the sample size just a tiny bit larger. Don't go nuts. Don't make it 1,000 or 2,000. Then you're going way beyond what's required of you. Be reasonable. Okay. Now, why do these pieces make sense? Well, what are some factors that will, literally some factors that will make the sample size larger? Well, the confidence level has an impact on what critical value we use. So for a larger confidence level, the larger critical value we use in here, and then the larger a sample size we'll need. So if you need a higher confidence level, you would expect to need a larger sample. Also, if the population exhibits more spread, then we're going to need a greater sample size to accommodate that. So if the population is more spread out, we're going to need more people or more ice cream cartons in order to adjust for that. So for example, if you have a very varied classroom of students, they're not just all coming from the same high school, for example. If you have a very varied classroom of students that come from many different high schools across the state, and it's a college class, then you may need a large sample size to accommodate that greater variability. But then, look here, the margin of error down here is in a denominator, and the larger the margin of error is, the smaller this will be. And the smaller the margin of error this is, the larger this will be. So if we want a smaller margin of error, if we want to shrink E, the margin of error, we need to raise N, the sample size. And bear in mind, this is all squared. So the impact is even more powerful than without the square. Math people might say that the sample size required varies inversely with the square of the margin of error. It's an inverse square property. Don't worry about that. All right. As I said before, it helps if this is greater than 30. But if it's not, then in order to use these methods, the original distribution better be approximately normal. So we have to add in that condition. All right, that's so that the CLT applies. If the sample size is big enough, if it's beyond 30, then we don't really have to worry about that normality issue. So let's do an example. All right, so in our example 2, our 99% confidence interval for mu looked like this, from 15.8 fluid ounces to 18.6 fluid ounces. That was a confidence interval for mu, where mu was the population mean amount of ice cream per carton. Okay, now notice that this interval is 2.8 fluid ounces wide in terms of the width of this interval. So the margin of error is half the width, or 1.4 fluid ounces. The overall width is 2.8. Half of that, the margin of error, is 1.4 fluid ounces. But let's say that we want to come up with a sample size to shrink the margin of error down to 0.5 fluid ounces. So we want to go now from a margin of error of 1.4 fluid ounces now to a margin of error of 0.5 fluid ounces. Let's say we're going to conduct a similar study tomorrow, like as a verification. What sample size would I need? So I'm going to replicate this experiment, but I don't want a confidence interval with a margin of error of 1.4 fluid ounces. I want to set the sample size little n. I want to determine the sample size little n, so I'm guaranteed a margin of error of 0.5 fluid ounces, assuming that I want, again, 99% confidence. A 99% confidence level. All right, and we'll interpret the result. It turns out that, again, for the 99% confidence interval, it helps that we're going to use 2.58 as our positive critical value. Because 2.58 and negative 2.58 will trap 99% of the Z distribution in the middle. That's a given hint. Okay, solution. Use the formula that I just showed you. The 2.58, the positive critical value, goes in here. The population standard deviation, we assume that was known. If it's not, then I'll show you ways around this. But 2.5 fluid ounces, we're assuming that that's known. The desired margin of error for the confidence interval, 0.5. That goes in the denominator here. And again, this fraction is squared, which tends to amplify the effects of these parameters. So we have 2.58, the positive critical value. Sigma is 2.35, that was given, over the desired margin of error, 0.5. You take that fraction, work it out, and then square it. Now that turns out to be 147.04, and even though this is really close to 147, remember, these symbols here tell you to do what? They tell you to round up to the next integer. That's to play it safe, to be a bit conservative. Or emphasis. So 148 cartons of ice cream. If we want to be guaranteed a 99% confidence interval for mu, where the margin of error is 0.5, so it's exactly 1 fluid ounce wide total, right? 1 fluid ounce wide total. 0.5 is the half width, the margin of error here, right? We're going to need about 148 cartons. We need to randomly sample, here's the interpretation, we need to randomly sample 148 cartons of ice cream to be 99% confident that the eventual sample mean will be within about 0.5 fluid ounces of the population mean, mu, the population mean amount of ice cream per carton. I'm saying here the eventual sample mean because we don't know it yet. We haven't conducted the study yet, so we don't have a sample mean yet. But we're setting things up. We're arranging it. We're not cheating because we're using legitimate statistics. It's just this time, instead of being given n and finding e, we're doing the reverse. I'm pre-specifying a desired value for e, and now we're finding the value of n, the sample size we need to accomplish that task, under 99% confidence. Next, we're going to talk about how difficult it is to reduce the margin of error, and it's harder than you might think. I'll give you a hint. It's because of the square. Next time.